Okay. So I think I'm the token industry guy in here. So I want to tell you about, I could go on about lots of things I've learned from Dick Karp, but I'm going to restrict myself to 5. And I'm going to try and explain each one of these vignettes in 2 slides. In one case, I think I go to 3. And along the way, highlight the contributions of some colleagues who are not here with us today. Okay, the first thing that everyone who knows Dick thinks about is the elegance of everything he does. Almost everything he does has some neat, elegant observation at its core. Okay? And I'm going to begin with the simplest of possible examples. Okay? This is something everybody in this room already knows, right? Which is randomized quicksort. So the way you sort numbers is to pick a random element from a set, compare everything in the set to it, and break it up to 2 sets, which I'll call smaller and larger, recursively sort each partition, and then stitch it together. Okay? And a crucial observation here is that once you do a split, nothing in the smaller set ever talks to anything in the larger set ever again. They are parted forever. Okay? And this continues. Okay? Now, if you go to the internet, you will find lots and lots and lots of analyses of the number of comparisons that quicksort takes. Many of them running into pages and pages of mathematics with sloppy constants and quarters and 3/4 here. I'm going to show you an analysis that I learned over 30 years ago. And I got these from handwritten notes from Dick Karp in 1983. And in some office move recently, unfortunately, I lost these notes. So if any of you has a copy, I'd love to get it back. Okay. All right, so here's the central observation. Right? So let's assume, for simplicity, and it's not a big oversimplification, that we are sorting the integers 1 through n. Okay? And so let's look at the event that I is compared to j. Okay? And that's all we're going to focus on here. Right? So a couple of observations. Anything outside the range between I and j is immaterial to this event. Okay? So the event I gets compared to j only depends on the choice of splitters between I and j. Okay? Now, if anything between I and j is selected as a splitter, I and j shall never be compared after that. Okay? They're permanently parted. Okay? So the only way I is compared to j is if one of I and j is selected as a splitter before anything in between. Okay? And of the I plus j minus 1 things in contention, there are only 2 choices that cause I and j to be compared. So the event xij, which is that I and j are compared, is true if and only if 2 of these j minus I plus 1 things happen. So that has probability 2 over j minus I plus 1. So the expectation of the indicator variable xij is 2 over j minus I plus 1. Adding this over all ij, or all I less than j, all ordered pairs, gives you exactly the expected number of comparisons. So notice that the thing near the bottom right is an equality. Okay? We don't have to mess around with unknown constant c here. Okay? And then if you want, you can bound it from above, the 2 times n times natural log of n. It's about 1.38 in log n, right? That's all.
I'm pretty sure I was not the first one to think of this proof. So another ingredient in my success is plagiarism.
Okay. So Dick invokes plagiarism in this one. I actually looked around the web, and the web is only finite, to try and trace down the origin of this proof. And after following a chain of steps, I found a comment from Avram Blum that attributed to my book, but I didn't get it from, I got it from these handwritten notes. Yeah, so I plagiarized from Dick, right? So what's neat here is the beguiling power of these indicator variables and linearity of expectation. And that's all there is to it. And that's something that you'll see a lot in Dick's papers and some other papers by other people whose work is similar, Joel Spencer, Noga Alon, and so on, right? It's surprisingly powerful, okay? So you don't need anything more complicated than this. All right, that was 2 slides. Next vignette, power of randomization. You could look at Dick's work and probably come up with over 50 examples that tell us of the amazing power of randomization. Right? And I'm just going to pick one. It's actually work that's by several people in this room, it turns out. I picked this because the power of randomization in this case is actually dramatic. Okay? So let me begin with the setting. Again, one that most of you are familiar with. It's the randomized caching problem. Right? So you have this thing called a cache that can hold k items at a time. Okay? And then you have a sequence of requests to items that are in the cache. Okay? And if the item that's requested is in the cache, you get it for free. Otherwise, you incur a miss. Okay? When you have a miss, the caching algorithm must make a decision. It must evict something in the cache to make room for the requested item. Okay? And so an online caching algorithm must make these decisions online with no knowledge of the future. And you want to compare the rate at which it misses to the miss rate of an offline algorithm that is prescient, that has infinite knowledge of the future. Okay? And so you look at that ratio, call it the competitiveness of your online algorithm. All right? Okay. So this was what was known before, was that no deterministic algorithm, including LRU and other commonly used algorithms, can, by this metric, do better than a factor of k. Okay? So no deterministic online algorithm has competitiveness less than k. And the way you do this is you have a universe of k plus 1 items. So k of them will fit in cache. One of them has to sit outside. And the adversary, having complete knowledge of the state of any deterministic algorithm, can always shoot at the item not in the cache. Okay? And so any online algorithm, any deterministic online algorithm must incur a miss at every single request. Okay? Whereas the offline algorithm can always look out in the future, see which one will be furthest to be evicted in the future, okay? And evict that one. Okay? So that lets it get by with a factor of k advantage over the online algorithm. Okay? Now what I'm going to do is describe the work in one slide that Dick and colleagues did to get a randomized algorithm. And it gets a dramatically better competitive ratio. And I'll motivate the intuition of why. Okay? So this is work by Amos Fiat, Dick Karp, Mike Luby, Lyle McKeough, Danny Slater, and Neil Young. Okay? And they call this a marking algorithm. Let me quickly describe the algorithm, and then I'll tell you why it gets such a big advantage. Okay? So the marking algorithm gets a competitiveness of 2 times the kth harmonic number. Okay? Now, crucial to this is the following modeling assumption, that the adversary specifies in advance the request sequence of items to be sought before the algorithm makes any random choices. Okay? So the only thing the adversary is unaware of is what random choices are actually made in an execution of the algorithm. Okay? All right, so here's the algorithm. So in addition to the cache locations, each location has associated with it a bit, a marking bit. Okay? All of these bits are initially 0, unmarked. Okay? Whenever there is a hit on a cache location, that bit gets set to 1, so there's a mark that's made there. And when there's a miss, in order to determine which item in the cache is evicted, you look at all the unmarked locations and evict one of them at random. Okay? And in this fashion, when all the bits in the cache get marked, you unmark them all over again, start all over again, and so the thing sort of proceeds in rounds of marking and unmarking. Okay? And I'm going to motivate the intuition of why the adversary is fooled in this, well, fooled to a logarithmic factor rather than, the way it works, again, is let's think of the case where there's only k plus 1 items, so one of them is sitting outside the cache, and the adversary is trying to shoot at that item to try and force a miss. Okay? The problem is, because the algorithm is randomized, the adversary cannot predictably identify the item that's outside. So the adversary is taking pot shots at the request sequence, and so tries there. No, that's already in cache. Mark it. Try that. Mark it. Try that. Mark it. And about halfway through these random shots is lucky and gets to that item that's outside the cache. Okay, this is intuition. This is not a proof. Okay, and this carries on. So each time you have the number of residual unmarked items, and by the time the round is over, the online algorithm has incurred about logarithmically many misses. Okay? And that's why you get this dramatic advantage, the fact that the adversary is oblivious to what is outside the cache. Okay? All right, dramatic improvement from a factor of k to logarithmic in k. My third vignette has to do with something Dick always taught us. Too many times we complicate analyses by early in the analysis making choices that are premature. So he would always say, defer your decisions in the analysis. Okay? I'm going to tell you now about the homework assignment. Actually, it was a midterm that he gave us many years ago. It's again an extremely simple setting that you'll all appreciate. And here it's more than the analysis. The algorithm itself entails deferral. Okay? So you want to search in a set of orderable elements. Okay? Think of them as the integers. Okay? So you're given the integers and a query queue, and you want to determine whether the query is in your set. Okay? Standard search problem. Okay? All right. So if you do not sort the set, if you do not pre-sort it, you've got to make n comparisons. You basically have to exhaustively compare your query with everything in each element in the set. Okay? Alternatively, you could invest n log n steps, build a search tree, and then each query can be answered with log n comparisons. Okay? All right. So what if the number of queries that you're ever going to answer is unknown? It's some number r. Okay? And you don't know this in advance. It could be small, in which case it really makes sense to not sort. It could be large, in which case it would have made sense to sort, right? So those of you who've thought about these things for a while are thinking of ski rentals and so on. Okay, so when is it worth sorting? Okay, you can show an information theoretical lower bound straightforward argument that looks something like this, that covers both the cases of R small and large. Okay. So the open question, I guess, we didn't realize it was open when he gave it in the midterm, was can you do optimal work for every R without prior knowledge of R? Okay? And the answer was a piece of work. I'm going to describe sort of the prefix of it, and then it went on to a number of other cases and other problems. This is joint work with Rajiv Motwani, is to build the search tree incrementally as queries arrive. Okay, so here's what you do. When the first query arrives, you compare it. You pick a random element, split it like you do in Quicksort. Okay? Determine which subset the query might fall into, go in there, and do this recursively. Okay? So when you're done, if life is fair, you've answered the first query with about 2n comparisons, okay, which is not too far off the best you could do. But at the end of answering the first query, you've got a partially built search tree, right? You've got this blob here, you've got two smaller blobs here, but wait, you've expanded one of the smaller blobs and smaller blob and smaller blob all the way down to the leaf, right? So on each subsequent query, as more queries arrive, you develop this partially built search tree, and after enough queries arrive, you've got a fully built search tree, okay? And if this happens, then you can show that with high probability, this matches the lower bound. Okay? You can also do this deterministically and more messily, but this is sort of the simple, clean way to do it. Okay? So by not doing upfront the work of building a search tree, you actually do about as well as you can. Okay? Now, Rajiv Motwani was a horrible procrastinator, and he summed up this work with great satisfaction by saying, never do today what you can postpone to tomorrow. Okay, the next story I'm going to tell you is one thing that struck me as a graduate student was we would have a large number of seminars. Speakers would come in from all over the world and give talks at Berkeley. And as I sat there in the audience, it struck me how intimidating it must have been for these speakers to have Dick Karp in the audience, because the speaker would go on and say, define the alpha, beta, x, y matching problem, and Dick would put up his hand and say, I think that trivially reduces to post correspondence problem or something like that. And the speaker shattered, right? So he had a way of seeing deep connections between things that were seemingly disconnected. And so to this end, I'm going to show you one such connection from problems in connectivity. Okay. Now, what I'm about to show you may look a little passé, but I want you to think back to the world of the 70s. So the problem is given an undirected graph and two nodes S and T. Determine if they're connected, right? And so, again, today we know a great deal about this problem, but back then, this wasn't a very well understood problem, especially if you have small space. So Savage had proven his theorem, and the question that Romas Alilinas, Dick Lipton here, Charlie Rakoff, and Lassie Lovas answered was, can we decide this in logarithmic space? And they said yes, in randomized log space, simply by doing a random walk from S. And after a while, you ought to end up at T. Well, how much time? About n cubed steps. Okay? And this may seem quaint now, because we know so much more about this problem. But back then, this was the state of the art. Okay? One thing this spawned was a cottage industry in this community on doing all sorts of neat things with random walks and undirected graphs. And I confess to being guilty of a part of that industry, right? And there is one result from there that I want to tell you about today. Okay? And this is strictly with having to do with random walks. Okay? Right, so we were interested in the hitting times of random walks and undirected graphs. Okay? And this happened one summer in the group of Ashok Chandra at IBM. Larry Russo and I were interested in how do you characterize hitting times? And the particular beast we were looking at was something called the commute times. So it's a time for a random walk to go from S to T and back to S. Okay? And one of the interns there was Roman Smolensky, and he did sort of a drive-by theorem. He walked by and he said, what are you guys working on? He said, we're studying the commute time. And it's the weirdest thing. It could be as little as n, and it could be as much as n cubed. And what is it in graphs that could possibly do that? And he said, oh, I bet it's the electrical resistance, and he walked away, right? And then the rest of us spent a few weeks deciphering his comment and deriving a lot of consequences. All right, so the thing I want you to note is there is a red box there with an equality in it. Okay, it's not a bound, it's not an approximation, it's an equality. Okay, what does the equality say? It says the expected length of a random walk from S to T and back to S is 2 times the number of edges times the electrical effective resistance between S and T, where every edge in the graph is replaced by a 1 ohm resistance. Now, if you've forgotten your high school physics, this may take a little bit of regurgitation. Okay? But this was, the kind of blinding insight that Dick would show in these talks, Roman Smolensky showed here. And the proof is actually fairly straightforward. You just realize that the system of linear equations characterizing hitting times on an undirected graph is exactly the same as Kirchhoff's laws governing the flow of currents in a resistive network. Okay? And that's all there is to it. Okay. Let me come to my last. Oh, and the one thing I would point you to is, if you've never looked at it, there's this beautiful monograph by Doyle and Snell that connects random walks in electric networks. It'll take you 2 hours to read it the first time, but then I would urge you to read it again and again, and it takes a while to sink in. At least it did for me. And it's absolutely gorgeous. All right. Now, we all think of Dick's prowess with combinatorics and probability, and the depth of his work. What many of us fail to recognize is that his work has tremendous practical utility and has continued to do that. And I've never figured out whether Dick seeks out utility in the work he does or whether utility somehow finds him. Right? And so I'm going to give you my final example from the world of computer systems. Okay? So the particular object here we worry about is something called distributed hash tables. Okay? And this is an extremely important primitive in large-scale distributed computing. Right? So you have these files, and they need to be stored somewhere at server nodes. Okay? And the basic primitive you get is you need to add files, you go to take away files, you go to access files efficiently. Okay? And all of this in an environment where servers can appear and disappear unexpectedly. Right? This may seem obvious, but many of us don't do the numbers. If a server is up 99.99% of the time, that looks great until you have 10 million servers. Okay? Then a lot of them are going down a lot of the time. Okay? All right. What do you want from such a system? It's got to be scalable. Okay? So when the number of users on the internet doubles next year, or the number of documents and files doubles next year, you've got to keep up with it. You have to have good performance. So you want, in a real environment, to get hold of files wherever they are in a couple of hundred milliseconds. Okay? It's got to be simple. Okay? The system should be something that doesn't take 2,000 developers to keep alive. Okay? And so the solution that I'm going to describe to you is work of Ratnasamy, Francis, Henley, Karp, and Schenker. Okay? And these, according to the paper, they were inspired by a Napster. So these are things called content addressable networks. So what was their idea? Right? What they said was, let's envision a d-dimensional torus. Okay? So each node gets mapped to a random point in this on this torus. And by a sequence of maintenance steps they detail, owns a rectilinear zone of the torus around its position. Okay? A file is stored is also similarly hashed to a point in the d-dimensional torus, and is stored at the node whose zone owns that, owning that node, that zone. Okay? Right. To get through the network from a requesting node to a node having a file, you just walk through these Manhattan zones. And the nice thing is each of these zones, each node, has to only connect to a constant number of neighbors. Okay? So that's a nice feature in the design. Sorry? Yeah, sorry. I was thinking of D. A small down points are just bigger of D, so where D is the number of dimensions. Correct. Right. As nodes arrive and die, these zones get split or coalesced through local updates. So that's a very nice property in terms of simplicity. You don't have to maintain any notion of a global state. Okay? Right. And if you want to get enough redundancy and durability and robustness, you ensure this by overlaying multiple toric spaces. Okay? And so you have several of these networks overlaid, and multiple hash functions. Okay? So that's great. You're probably thinking, well, I never thought of Dick as a Napster kind of person. So where do these ideas actually get used, right? Now, my day job entails taking care of a bunch of large services like Gmail and Google Drive. And without getting to the exact numbers, the number of files we think about has at least 4 commas in it. Okay? And I don't know if that's probably lost in the Europeans here, but that's in the trillion plus range. The number of nodes is in the million plus range. Right? So without getting into exactly how this is implemented, these ideas are extremely influential. And if you look at the picture I'm about to show you really, really hard, you'll find Dick's work in there. Thank you, Dick, for all you've done.